This video discusses the major characterization techniques used in nanotechnology. In this module, we will discuss the different characterization methods that are used to visualize the nanomaterials that are between 1 to 100 nanometers in length. If you enjoyed watching this video, please like, subscribe, and share this video so that you can be notified of new videos that I post on this channel. The transmission electron microscope, also known as TEM, is one of the most fundamental tools for visualizing nanoparticles of different sizes and shapes. The technique uses a beam of electrons transmitted through the ultra-thin specimen to form an image. Since electrons have much shorter wavelengths than visible light, it can achieve much higher resolutions than a light microscope. TEM can also give 2D size and shape information about the nanoparticles. The level of magnification power is different for different models, and also a HRTM can resolve and image much smaller nanoparticles, if necessary. TEM can be used to visualize the size and shape of metal, magnetic, semiconductor, and carbon-based nanomaterials. The image on the right side of the page is an example of how a TEM instrument looks like. Nowadays, digital imaging is directly integrated with the TEM software, making image acquisition very easy to handle. The TEM image comes with a scale bar, so you can measure the size of the nanoparticles. The normal sample preparation for TEM analysis is to use a formvar stabilized copper TEM grid and place 1 drop of a dilute solution onto the nanoparticles and allow the drop to air dry on the grid. Electron diffraction patterns are especially useful if you're trying to figure out the specific crystallographic facets that are present in the nanoparticles. The electron diffraction patterns can be obtained either by using a TEM or a HRTM. The patterns give information on the specific crystallographic facets that are present. For example, tetrahedral nanoparticles are composed entirely of 111 facets, while cubic nanoparticles are composed of entirely 100 facets, and nanorods contain 110, 100, and 111 facets depending on the location of the nanorods. High-resolution transmission electron microscopy, HRTM, is used to image lattice fringes which reflect the periodic arrangement of atoms, and also to image very tiny nanoparticles that cannot be seen on a standard TEM. It can also be used to obtain electron diffraction patterns. The image on the right shows an example of a HRTM. Energy dispersive spectroscopy, EDS, is a tool available on a TEM or a SEM which allows one to obtain the elemental mapping information. EDS works by detecting X-rays emitted from a sample when it is bombarded by a focused electron beam. High-energy electrons from the TEM or SEM strikes atoms in the sample. Then, an incident electron ejects an inner shell electron from an atom from the K or L level. An electron from a higher energy level drops down to fill the vacancy. This transition releases energy in the form of a characteristic X-ray specific to the element. The EDS detector measures the energy and intensity of these X-rays. By using EDS, it is possible to determine which element is the core element and which is the shell element. Scanning electron microscopy, SEM, is a technique that can obtain 3D images of nanoparticles, so you can visualize the three-dimensional shapes and morphology of the nanoparticles. In addition, there are high-resolution scanning electron microscopes, HRSEM, which have become available. This allows for 3D imaging of the nanoparticles. It can be used to image a wide variety of materials like metal, semiconductor, and magnetic nanoparticles. Sample preparation for SEM and HRSEM is different than for TEM or HRTM. For SEM and HRSEM, it is necessary to use a SEM stub and affix a sticky black carbon tape onto the stub. Then the sample needs to be placed on the sticky top side of the black carbon tape. Once that is done, the sample is ready for SEM or HRSEM analysis. AFM stands for atomic force microscopy, and it is another technique that can provide 3D information on samples. AFM works by scanning a sharp tip mounted on a flexible cantilever over a sample surface. The tip interacts with the surface via forces such as van der Waals, electrostatic, or repulsion contact forces. These interactions causes the cantilever to deflect, and these deflections are measured. For AFM measurement, substrates such as gold on glass, or other types of substrates are used. There are 3 modes for AFM: contact mode, non-contact mode, and tapping mode, which is also known as intermittent contact mode. It can be used to image a wide variety of materials such as DNA, proteins, and nanoparticles. However, TEM and SEM are much more popular tools to use for characterization of nanoparticles. TEM is used to image many kinds of nanoparticles, and also it is possible to obtain electron diffraction patterns, as well as conduct elemental mapping to find the composition of your core shell or bimetallic nanoparticles. HERTEM is mainly used to obtain lattice fringes and image extremely small nanoparticles not visible using a standard TEM. SEM and HRSEM are used to obtain 3D information on the nanoparticle shape. AFM also provides 3D information on the shape of the nanoparticles, and there are 3 modes: contact mode, non-contact mode, and intermittent contact mode. If you enjoyed watching this video, please like, subscribe, and share this video below so that you can be notified of upcoming new videos that I post.